Hey, everybody. So I'm going to go over a few details from the last class and then talk a little bit about some topics that we'll be covering in the next class. So that would be lectures 3 and 4. And the old stuff really refers to determining if two events are statistically dependent or independent. And so I kind of wanted to elaborate on that a little bit because I think maybe some of the things I said could have been misconstrued or a little bit confusing. So I just want to make sure that that's clear. And then we'll be talking a little bit about Bayes' theorem some more and a little bit about the theorem of total probability. So that's the plan. So let's go ahead and get our screen share going, and we'll get the lecture on the way. Okay. So let's start out talking a little bit about how you determine whether two events are statistically dependent or statistically independent. And we've talked about this qualitatively quite a bit, and you probably, or you might have figured out how to actually determine it quantitatively, but I kind of wanted to follow up and make sure that that point is clear. So let's look back at the example we were talking about at the end of class last time. So remember, we had this situation where a city was being supplied electrical power by two power plants, and the failure of one or both of those power plants would essentially lead to a brownout in the city. And we defined two different kinds of events. The first event, event A, referred to the case where we had a failure of plant A, and then the second event referred to the situation where we had a failure of plant B. And the probabilities of those two failures are shown there. Probability of A occurring is 5%, and the probability of B occurring is 7%, and the probability of both A and B occurring is 1%. So then the question is, are these events independent? And this question came up during class, and I kind of gave a hand-wavy argument about, well, you know, if you think about it, maybe these plants would fail independently, because why would one depend on the other? It's not clear. But on the other hand, you can think of situations where that might occur. For example, maybe they fail if there's too much demand for electricity. And so if one fails, then the other one's very likely to fail because all the electricity demand is going to go to the other one. So in that situation, in that scenario, the failure of plant A, for example, the probability of that would absolutely depend on the occurrence of failure of the other plant, plant B. And so, so that would be a case where we would have statistically dependent events A and B. You can also imagine that maybe they fail if they're subject to an ice storm. So if an ice storm comes in, both plants are more likely to fail, and so that means that the probability of the failure of one is going to go up if the other one has failed, just simply because both are experiencing the same ice storm. So anyway, the bottom line is that it's not at all clear that these events are statistically independent, like I was kind of arguing in class. And you can think of scenarios where they would be independent, and you can also think of scenarios where they would be dependent. And so that kind of leaves us with a situation where we would really like to, in fact, require the ability to compute or determine based on the probabilities that are given to us whether these events are statistically dependent or independent. And so that leads to the question, for these two events, A and B, are these events independent, and how would we determine that? Well, luckily, we can, and it really goes back to statements of conditional probability and the product rule, which are really they're the same equation, just rearranged. So remember that by kind of definition, if two events are statistically dependent, then the probability of A depends on the occurrence of B. So that means that the probability of A occurring given the event B occurring is not just going to be equal to the probability of A occurring alone, or without any knowledge about the occurrence of B. So one way to test for statistical dependence is to look, if you had information about, say, the probability of A conditioned on B, compare it to the probability of A, and then see if they're equal or they're not equal. In this case, if they're not equal, then we can conclude that they are statistically dependent. A and B are statistically dependent. Maybe a little bit more straightforward way to look at that is just to simply rearrange this equation into the product rule. So now we have the probability of the intersection of A and B, so both of them occurring, is going to be equal to the conditional probability of A and B times the probability of B. And exactly what we said here, if they are statistically dependent, then we can't just replace this conditional probability with probability A. And that implies, oh, let me grab my little pointer doohickey. That implies that the probability of A intersect B is not going to be equal just to the product of probability A and probability B in the event that we have two events which are statistically dependent. So that's another test. Conversely, if we have two events which are statistically independent, that is, the probability of A does not depend on the occurrence of B, then if we think about this conditional probability, because probability of event A doesn't depend on the occurrence of B, this conditional probability just has to be equal to the probability of A. Likewise, if we go back to that product rule, if they're statistically independent, then that means the conditional probability of A on B is just probability A. And so in that event, the probability of the intersection of A and B is exactly equal to the probability of A times the probability of B. So armed with that information, let's go back to this example and determine whether these two events A and B are statistically independent or dependent. Remember, if they're independent, then we would expect that if we multiply the probability of A times the probability of B, it should equal the probability of A times B. And so if we do that, we take the probability of A, probability of B, 0.05 times 0.07, multiply those two together, we get 0.0035, which is definitely not equal to 0.01. And so we conclude that these events are not statistically independent. In other words, if one event occurs, it will definitely affect the probability of the other event. So are these events independent? No. So my hand-wavy argument in class was actually wrong. Okay. All right, so that's really all I had to say about determining statistical dependence or independence. And now I wanted to transition to a few fun, maybe the last fun facts associated with chapter 2. And one of those fun facts is what's called the theorem of total probability. And basically, here's what the theorem of probability, total probability says. So consider that you have n events, E1 through En, and we're going to put some conditions on those events. We're going to assume that they're mutually exclusive, so the probability of their intersection is equal to 0. They can't occur together. And they're also collectively exhaustive, so if we took the union of all of those events, E1 through En, we would end up with the possibility space. So they completely cover the possibility space together. And so the theorem of probability says basically then if event A is in the sample space, we're going to have the following result. That is that the probability of A is going to be equal to the probability of A conditioned on first event times the probability of the first event plus the probability of A conditioned on the second event times the probability of the second event, so forth and so on until we get to the nth event, probability of A conditioned on the nth event times the probability of the nth event. Or in summation form, we have this equation here where we're just summing up over the different events E1 through En. I'm going to save the Venn diagram for a little bit later when we go through the proof first. So here's the proof for the theorem of total probability. So let's just start with the event A. The event A is going to be equal to the intersection of A and the possibility space S, just because if we intersect S with the event A, we just get back A. And because these events were collectively exhaustive, that means that we can re-express S as the union of E1 through En. Okay? And then we can distribute that event A through the parentheses. And so we end up with A intersect E1, union A intersect E2, and so on to A intersect En. And so we can take the probability of both sides of this equation, and because these events are mutually exclusive, that means that the probability of A is going to be just the sum of these events. We don't have to worry about cross terms or anything. And now we have on the right-hand side these terms that involve the probability of the intersection of two events, and so we can use the product or the multiplication rule to express them in terms of conditional probabilities. And this, my friends, is exactly the theorem of total probability. So that's how it was derived. Note that really there's an equivalence between stating that the probability A is just the probability of the intersection of A with all of these events summed together, and then the probability expressed in terms of the conditional events. So there's really an equivalence between these two statements, and that's going to become important in terms of the graphical interpretation. Again, the probability A can be expressed as the probability of the intersection event of between A and event 1 plus the probability of A and event 2 and so forth. Or we can re-express that using the multiplication rule in terms of these conditional probabilities. That becomes important when we sort of interpret graphically or in terms of a Venn diagram what's going on. And so here's a nice Venn diagram which basically shows the possibility space as a rectangle. So that's our S, the rectangles are S. And then within S, we have this event A, which is indicated by the ellipse. So the whole ellipse is event A. And then the possibility space is divided into a series of events, E1, E2. So this is event E1 here. And then E2's here, E3, and so forth to En. And we can see that the total probability of A, which is kind of represented by the area here within the possibility space of this ellipse, can be expressed as the sum of the intersection between A and E1, which is this hatched area, plus the intersection of A and E2, which is this double hatched area, the intersection of A and E3, which is this weird hatch, and then the intersection, finally, of A and event En, which is the square hatched. And so we sum those together, we get the total probability. So that's sort of, from a graphical perspective, that's a restatement of this expression or this equation right here, that the probability of A can be just represented as the probability of AE1 plus the probability of AE2 and so forth. On a kind of deeper level, this expression here is kind of getting to the conditioning of A and with respect to each of these events. And you might have a little trouble kind of visualizing what these conditions look like in a Venn diagram kind of scenario, but maybe it'll be a little bit clearer here. So again, we can express these, the sum of the intersection of events as these conditional, sum of these conditional probabilities multiplied by the probability of the event. So what we're really doing is we're taking the probability of A, so the entire A here, but conditioned on E1. So just, we're basically reducing the possibility space to just be E1 instead of the whole thing, times the probability that E1 occurs, right? So that would be the first term in the sum. And likewise, the second term in the sum is going to be, again, the probability of overall A conditioned on just this portion of the possibility space times the probability of that event 2, and so forth and so on. So it's just basically two different ways of representing the same area, which is this event A here in the possibility space. Now, we talked a little bit about Bayes' theorem last time, and Bayes' theorem can be related to the theorem of total probability. And let me show you how. So here's the theorem of total probability. We just derived that. And essentially what we're doing is each of these terms in the sum on the right-hand side is asking what is the probability of event A conditioned on the various events E1 through En. So that's the term here. And there's lots of situations where we want to know the probability of one of those events given the occurrence of A. In other words, we kind of want to flip these two, we want to flip EJ for A. And so how do we do that? So Bayes' theorem allows us to do it. It basically says if we want to know what the probability event EI is conditioned on A, it's going to be equal to the probability of A conditioned on EI times the probability of EI divided by the probability of A. And we derived it last time, but let's go ahead and go through that process now. Remember, we can express the probability of the intersection of A and EI is equal to the probability of EIA. We're just using the commutative rule here. Doesn't matter how we arrange the intersection of the events. And then we can apply the multiplication rule, the product rule, to each of these terms, the left term and the right term. And so we end up with, on the left side, probability of A conditioned on EI times the probability of EI. On the right side, we get the probability of EI conditioned on A times the probability of A. Straightforward. And then we solve for the probability of EI conditioned on A. So we solve for that to take this probability of A term and bring it over to the left-hand side, then switch the left-hand side and the right-hand side to solve for the probability of EI conditioned on A. And so this is our Bayes theorem. And somebody came up to me after class and said, hey, you wrote it down wrong. So if I did, my apologies, but this is actually Bayes theorem. So this is the theorem you should be working with. So we're going to be applying Bayes theorem to a couple different kinds of problems, and homework 2 is really going to kind of center on that. But I wanted to start down that road by sharing with you one problem that we're going to explore a little bit more deeply in class on Friday. And here's the problem statement. So we've got aggregates for the construction of reinforced concrete, I don't know what the building there is doing, are supplied by 2 companies. Company A delivers 600 tons of the aggregate per day, while Company B delivers or supplies 400 tons. So it looks like there's a total of 1,000 tons delivered a day. 60% of those are coming from Company A, 40% are coming from Company B. From prior experience, so that's a prior, it is expected that 3% of the aggregates from Company A are substandard, while 1% of the aggregates from Company B are substandard. And then we're told to define the following events. Event A is the case where aggregates are supplied by Company A. The event B is the event where aggregates are supplied by Company B. And event E is the event where aggregates are substandard. And so the first question that we're asked is, in words, describe the difference between the probability of E given A versus the probability of A given E. So let's think about that a little bit. So the probability of E given A, so what is A? A is that the aggregates are supplied by Company A. So we're asking, what is the probability that the aggregates will be substandard, that's E, given that they came from Company A? Well, actually, we were given that information because the problem statement says, from prior experience, it is expected that 3% of the aggregates from Company A are substandard. So we know that if the aggregates are from Company A, that's our conditioning, that the probability that they will be substandard is 3%. So the answer to this is 3%, or 0.03. What about the probability of A given E? What does that mean? Well, in this case, we're conditioning based on E, which is that the aggregates are substandard. So we basically find that some aggregates in the 1,000 tons that we had delivered, that some aggregates are substandard, some sample of that delivery. And we want to know the probability that those substandard aggregates came from Company A. So it's very different. It's not 3%. It's very different than this statement here. Basically, in this case, we know that the aggregates are substandard, and we want to know the probability that they came from A, where in this case, we know they came from A, and we want to know the probability that they're substandard. And in order to calculate this term, we actually have to use Bayes' theorem, which we'll be doing in class. So with that, I will conclude the lecture, and I'll see you tomorrow morning at 10 in the morning. Okay, thank you.